Okay, so morning everybody. So it's a bit of a delay here. Fine. So just to show you how to navigate around the material, this is the ARCHER2 home page, the ARCHER2 training page. And if you go to upcoming training, you will see the advanced MPI course is this one here. That's the generic page, but what's been added quite recently is the course materials. So if you go to the training course page, go to course materials, you will see that a slightly scrappy markup page. I have put in the timetable. So the first talk I was going to give was the tips and tricks. So we're doing 10 till 4 each day. I've tried to tailor it to what people said in the survey. I'm pulling material from a bunch of different sources here, so hopefully it may not flow 100% smoothly, but hopefully it'll make some sense. So these links will link to the material. These are links to the PDFs of the material. For example, that's the that's the course we've just had. The exercise material I've got down here. Now we're not going to do any exercises till after the first coffee break. I don't think. In fact, actually, till after lunch. But the exercises are here. They're slightly. We'll go through them, but this should be all the material. It's not particularly brilliantly arranged, but hopefully should make sense. So the first exercise we're going to do actually is after lunch, is do a ping pong, and that will hopefully illustrate some of the topics I've covered in the MPI internals. But a lot of people wanted to have the sort of tips and tricks lectures. That's what I'm going to give first. So hopefully that's where the material is. Just to go back, the main ARCHER2, ARCHER2 training, upcoming training. You'll see the link to the advanced MPI, and then go to the course materials. And this is just a standard. This is a GitHub page, which hopefully explains everything. So this tips and tricks lecture is actually one of the last lectures I give on my message passing course. However, I have run a shorter of the introductory message passing course. I run a slightly shorter version of that these days, so I don't give that in that session. So hopefully I'm not repeating material that you've already known. If you have heard this talk before, this is one of the talks I do update relatively frequently. So let's okay. So please, now this is basically, you've written MPI programs, hopefully written a few yourself, and this is going through sort of tips and tricks. Please comment on these. Please ask questions. We're going through this. This is rather a butterfly collecting of different kinds of topics and such like, but hopefully it is interesting. So. Okay, there's a bit of a delay, but there we are, message passing program. Tips and tricks. So, what are we aiming to do? Well, we're aiming to write correct MPI programs, obviously, that are portable to many systems. You want software is much longer lived than hardware, and so you want your code to be portable, easily portable to many systems. You want to be efficient, and you want to be easy to maintain. And so this talk is a sort of a mixture of sort of software development and MPI specific tips and tricks. So please ask questions as we go along if you have any issues. So these are the kind of things which I have sort of come across that people have problems with, and they kind of cover all these in the talk. Common problems in MPI. Assuming MPI send is asynchronous, that causes non-portability. I'll cover that. General non-portability issues. Program with specific process counts. That's something which people do as beginners, but I'll cover that. Issues with collectives. Again, that's maybe a bit basic, but I'll cover it quickly. Incorrect use of non-blocking is a very important one. I see that quite a lot. Sending lots of small messages is an issue. Array allocation issues in C is always an issue. C is pretty terrible for the way it has support for arrays. C++ is probably a bit better, but you get issues here, and I'll talk about that. Array syntax issues in Fortran I may not cover. This is one of the things I actually wanted to cover in the what people did. So I'm actually going to start a quiz here, I would just get a feeling for what. So this was one of the questions in the more. Okay, so that is useful to know. So full disclosure, I'm not really a C++ programmer, but then MPI isn't a C++ interface. So please correct me if I. But I'm so that's very interesting to know that half people are Fortran programmers. Okay, so I will cover. Thank you. I will cover the array syntax issues in Fortran. That is interesting. Thank you very much. That was very useful. And code readability and general debugging problems. So we'll cover this when we talk about MPI internals, to maybe motivate why this is. But one of the issues about MPI is, if you're learning message passing for the first time, you'd ask, how do I send a message? And someone says, well, use MPI send. And then you would ask, well, is it synchronous or asynchronous? If I issue an MPI send and there is no receive, does the program deadlock or not? And the problem is that you don't know. MPI, for reasons known to itself, which I will try and motivate a bit later, doesn't define if MPI send is synchronous or asynchronous, if it's like sending a letter or making a phone call. And this can cause, so a lot of people assume that MPI send is asynchronous. They assume that MPI send will be like sending an email, be a fire and forget. Now that is often true for small messages. Okay, for small messages, MPI send will tend to be asynchronous, meaning it will be buffered. What will happen is MPI will say, okay, David's sending a small message. I'll take a copy of that message, squirrel it away, and send it later on. So that means there's less likelihood of deadlock, because you don't have to have a receive pending. However, that's not guaranteed. So you should always program as if MPI send is synchronous. You should always make sure a receive is posted at the time you post MPI send. A lot of people forget that. And the problem is that typically small messages are buffered, but large messages are not buffered. This threshold varies with implementation. So your code may run on one machine and deadlock on another. And so, this is a real problem. So you really have to worry about this for portability. A correct code will run with all MPI send calls replaced by MPI send. MPI send is synchronous send. It's guaranteed to be synchronous. If there's no receive posted, it will wait and then potentially wait forever. And so, that is a big issue. You can ask for MPI to do an asynchronous send, a buffered send with MPI B send, but it's really rather a horrible routine, and it's not very widely used. It's in the standard. It's not very widely used. It's a nasty routine for various reasons. But this is a major portability problem. So one of the classic reasons when people, whoops, today, sorry, I don't know why I was doing that. One of the classic reasons where people say there's a bug on your machine and my program runs on this machine but not on yours is because they've assumed MPI send is asynchronous. And we'll cover in some. When we look at the internals, why MPI decides not to define if MPI send is synchronous or asynchronous. Data sizes, it's not such a big deal now when there are so few compilers and hardware and operating systems. 15 years, 20 years ago, when there are lots of different compilers, so for example, it used to be on Cray systems, a real was 8 bytes. Was like a real was on a Cray system, or a float on a Cray system was what everyone else would call a double. But be careful of data size or layout. Be careful of compiled and padding infrastructures. So it's just a general. It's just a general comment. Try not to assume that integers are 4 bytes, or that reals are 4 bytes, or doubles are. Well, there are various runtime inquiries. The thing which I do see that people do fairly badly is they write a program which uses floats or reals, which are single precision, then they want to convert to double precision. So they have some magic flag, minus convert floats to doubles, or the equivalent in Fortran. That's not a good thing to do, because of course in an MPI code, not only do you have floats and doubles or reals and double precisions in your as declarations in your language, you also pass them to MPI calls, and you have to then pass MPI float or MPI double or MPI double precision or MPI real. And so, if you want a code which runs in both single and double precision, for example, you can't use magic compiler flags, because you also need to change the MPI definitions as well. And I would say the right way to do this, if from the start you want to write a code which can be in single or double precision, or heaven forbid half precision, you're doing machine learning, it's easiest thing to do is to use an include file. So what you do is you have a header file, an include file. I can see there's a question here, sorry. I'm slightly struggling for screen spacing on my laptop, so apologies. Okay, so no. So Mark has asked about MPI ISEND. No. So the correct way to avoid deadlock is to use MPI ISEND. Okay, that is the right thing to do. Okay, so we'll cover that a bit when we look at performance and such like. But MPI ISEND is the right thing to do. Okay, because MPI ISEND will avoid deadlock by being in MPI terms non-blocking. So, however, you will probably get, if you just use MPI send, you will probably get away with it for small messages, because you will not get deadlock. Okay. However, to safely program with MPI send and guarantee your code is deadlock free, then in practice you will have to use MPI ISEND. It's a slightly subtle thing. It's one of the annoying things about MPI, that one of the most basic questions you ask is the send routine synchronous or asynchronous? Does it wait or does it not wait? Is undetermined. But yes, MPI ISEND is the right way to program. Does that make sense, Mark? But that
yes,
is the
it's fine. Yeah.
But what a lot of people do is they don't use ISEND, they use send, and they get away with it because they've got small messages, and then they run a big problem, or they run on a different machine, and the code suddenly deadlocks because they have incorrectly assumed the MPI send. The MPI send, so I have to be careful, that the blocking form MPI send is asynchronous. So if you want to do, what you should do is you should have a header file of the equivalent in C++, I guess, but in C you would do type left float real number, and nowhere in your code do you say float or MPI float. You say hash define MPI real number MPI float, and then you say type their float real number. And so when in your code you do real number x, which here is a float, and you do MPI routine and you pass MPI real number, which is also an MPI float. But if you want to change to double precision, you just change these two numbers, these two definitions in the header file, recompile, and the whole thing works for you. So I'm not a fan of using magic compiler flag, because of course again the compiler flags are by definition compiler specific, and those flags may not exist in a different compiler. In Fortran is a very sophisticated type system, and you do the same thing in Fortran. You would have a module which defines the precision. You would have a real number, an MPI real number, and you would do something like this: use precision, real kind equals real number x, MPI routine x, MPI real number, and these are then defined as here single precision. But it'd be a trivial change to change that to 1.0 denote that to MPI double precision, and your code then compiles and runs in both precisions. And there's a lot of reasons why I think this is good. You may say I only ever want to run in double precision, but actually reproducibility stroke verification is a real problem in scientific and technical programming, because you're using floating point numbers which aren't guaranteed, and you'll typically get different numbers of processes, different numbers on potentially different compilers which rearrange things. So the question with my code correct is a subtle one. And when people get small differences, they often say that's rounding error. Well, how do you know? Okay, so if you can change the precision, so if you normally run a double precision and your results differ by 1 part in 10 to the 5 or 10 to the 6, you might say that looks like rounding error, but it could just be a bug. If you can then run the code in single precision and that error gets larger, that gives you evidence that it is a rounding error. If the error stays the same, you've just got a bug. Okay, and I always say people think that 1 part in 10 to the 6 is a small error, okay, but it's not. If you have arrays which are 100 by 100 by 100 and you get one, you have a 3D problem with arrays that are 100 by 100 by 100, that means there's a million elements in each array. If you get one of those wrong, which for example, you do a halo swap and you miss one of the halo entries, okay, that is a difference of 1 part in a million, 1 part in 10 to the 6. So people are much too quick to say, oh, that's okay, it's just rounding error without any evidence, but that's a slight aside. Non-portability, correct C code or Fortran code should compile with any C compiler or Fortran compiler, and also therefore a correct MPI code should also run correctly with any MPI library. And the problem is that people often, well, I do as well, people often develop and debug and verify their programs on their laptop where they might be using OpenMPI, for example. But then you go to you port to another system like ARCHER2, and it's not using OpenMPI, it's using MPI, which is based on MPI CH2. So you might think that running on more than one machine is a good test. You know, I've run this code on my laptop and I've run it on an HPC cluster, but actually many parallel clusters will use the same open source MPI. Here you're not really testing is the hardware different. You're testing is the library different. Running on 2 different HPC systems may not be a good test. Okay? So you may have assumed things in your code. You may have assumed a certain behavior of MPI, which might be true in one library but not another. It's just like saying in a Fortran or a C code, integer I or int I, and assuming that I is set to 0. It's not guaranteed. You might be lucky. It might be set. A particular compiler might be kind to you and set default integers to be 0, but then it's not guaranteed. And so just like you should always check the portability of your program by compiling on different compilers, you should check the portability of your MPI program by running on different MPI libraries. And to be honest, one of the nicest things is you have more than one implementation on the same machine. Now, unfortunately, on ARCHER2, we're locked to a large extent to Cray MPI. But you know, if you have your laptop, install MPI CH2 and OpenMPI, and then or use Intel MPI. It's a really, really good development methodology to regularly check your program is correct when running on different MPI libraries. Code readability, this is a big one. Adding MPI can destroy a code. We would like to maintain a serial version because we'd like to say, well, what's the correct what's my correct answer? My parallel program gives this answer. What's my correct answer? Well, it'd be nice to say, what do I get in the serial code? It would be nice to compile and run identical code without an MPI library. Actually, I don't mean running with an MPI code with P is the number of processors. I don't mean running with MPI code with one processor. I mean running without an MPI library. So for a whole bunch of reasons, what you should do, and this is a really important software development approach, is you should separate your communications into a separate library. So what I'm saying is your code should not be sprinkled with hundreds of MPI calls. It should have a small number of meaningful calls. So what you say when you write your code is, okay, what parallel operations do I need to do with my program? I need to do global sums. I need to do halo swaps. I need to do gathers. So you write a routine called global sum, halo swap, and gather, and you implement that using MPI. You don't scatter random MPI calls to write your whole code. And that has a whole bunch of advantages. And so there's no explicit reference to MPI in your main code. And what it allows you to do is to actually provide a dummy library for the serial code. If you go the whole hog, you can actually then have a library which allows you to compile and run your program in serial without access to an MPI library at all, which is also a nice thing to do. So I have an example here which I did with Fortran, but I do have a C example later on. So for example, okay, If you want to initialize an MPI program, you have to call MPI init IERA. You have to include a header file. You have to do MPI com size and MPI com rank. Okay, that all MPI programs start like that. Okay. Well, that's really nasty, horrible code to have. I mean, that's nice to have a routine called power begin. Okay, so this Fortran routine, my Fortran program here, this comes from something I wrote a long time ago, had a function called power begin, which returned the size, i.e., the number of processes, and the proc ID, the ID of the process. And in fact, in this program, I got sick of the fact that MPI refers to processes starting from 0. So in my main program, I referred them from 1. I actually added once the proc ID and obviously subtracted it off later on. And then, for example, for your serial machine, this is just a completely dummy routine. But you should not have random MPI calls in your main code. Here, your main code goes call power begin, and that looks much nicer than these 3 rather meaningless MPI calls. A global sum, okay, if I want to do a global sum of a single double precision number, I have to do MPI or reduce of the value into a temp, because by default we can't use the same one. It's one MPI double precision, MPI sum com. Com was defined elsewhere as com world IERA. This is really vastly overcomplicated syntax. What I really want to do is have a function with this subroutine, call it par d sum, a function which does a parallel double precision number. A parallel sum of double precision number. And if I know I'm always using com world, if I know I'm always using doubles, and I only want a single scalar here, I can make the call in the main program much more readable. Okay? And then for the serial machine, of course, I return nothing. Okay? I don't need to do anything here. So my main code, when I want to do a parallel double precision sum, just in Fortran, call par d sum of x, which is much nicer than MPI or reduce x 10 1 MPI double precision MPI 7 MPI com world IERA. Okay, so that's much nicer. And then in your make file, if you're a CMake person, be more sophisticated than this, I have my, and for reasons unknown only to myself, I actually had 2. I squirreled away my MPI functions in 2 routines, dem parallel and dem coms. But basically, my sequential source, this code here, had no explicit call to MPI. I had routines called to halo swapping, power init, power d sum. These routines were defined in MPI source. But I also had a fake source, and I just said parallel source is fake source for MPI source. I could compile up a serial or parallel program from the same source with a very small change. Now, this is something it's almost impossible to retrofit, but it's a very good design decision to take right from the start. So, and in C, ugly code, MPI init null. Null, this is particularly horrible in C. MPI init, a nicer code, you do power begin size rank. Okay, this is much nicer to do. Okay, and then you basically implement that with these in this. So your main code just has power begin size rank, and it's implemented in MPI. And of course, this is a bit of a trivial example, but it becomes much more useful when these are message passing operations like like summation, but also halo swapping and such like. So again, yeah, rainfall is power d sum of rainfall is much in Fortran is much more sorry, in C, but it's a C example. Rainfall is power d sum of rainfall is much more say I've got a climate modeling code is much more readable and useful than this kind of stuff here. Okay, and so if you have a comment globally sum the parent double precision rainfall value, rainfall is power d sum of rainfall. That makes sense even somebody who's not a parallel programmer. Whereas this, this is just gibberish. Okay, so again, it makes your code much more readable to all and sundry. Again, this is just an example of the make file. So why is putting all your MPI calls in the library worthwhile? Well, if you really gun for it, you can compile a serial program from the same source. It makes the parallel code much more readable. And for example, if you're concerned that some of your imagine you think I think that somewhere along the way my double precision my reductions of my double precision variables are getting funny results. if you have 100 calls to MPI all reduced in your code, you then have to put debug statements into 100 lines. If you funnel all your MPI all reduces through one of your own functions, you can just add debugging to that function. On entry, say, the input value on rank this is that, and the output value is this. So it makes debugging much better. This is not such a big deal now, but definitely in the old days when MPI wasn't necessarily completely optimized everywhere, it enables the code to be ported to other libraries. Imagine someone said, oh, on the Cray, there's this really, really fast, hand-coded, super fast routine for doing double precision global sums. You don't want to replace 1,000 calls to MPI reduce with this magic Cray routine. But if you funneled all your MPI or reduces all your reductions through your own routine, you can just change that. Okay. And again, we'll see this later on. We do halo swapping. If I want to swap halos, should I use send, bsend, isend, issend, des, whatever? There's 100 ways of doing it. If you funnel all your halo swapping calls through a function called halo swap, you can then basically, whenever you port your code to a new machine, you might have half a dozen implementations of the halo swapping, all done in slightly different ways, and you can pick the one which is fastest on your target machine. So you can optimize your comms for different MPI libraries. Okay, one MPI library might be best to do one method of sending, on another it might be best to do another. So that's a general design, and this used to be very common in the old days when you didn't even know you had MPI. You didn't even know what your message passing library was going to be. So you funneled all your communications through your own interfaces and then implemented them with other. Now MPI is universally available. There's a temptation not to do this, but it is still a good discipline and programming technique. This is something which, this is a simple error, but not calling collectors correctly. You have to call collectors with all processes in the communicator. People, when they're learning MPI, would do this. If rank equals 0, MPI bcast, that's not correct. You have to call you have to call a collective on all the process. And obviously, if you did if rank equals 0, call an all reducer, would call deadlock. But this is another. Sometimes people use reduce in the sense. So if you remember, all reduce is a global sum where every process gets the answer. In reduce, you specify a root process. You might say, well, only rank 0 needs to know this summation. I'll call reduce and just have rank 0 know the answer. The problem with the way that you program MPI, which is an SPMD model, single program, multiple data, if you have a variable called, let's say, global rainfall, okay, that variable exists on every process. If you compute it with a global sum, but only place the answer on a rank 0, then you have a variable called global rainfall, which only makes sense on one process. Now, you may remember that when you write the code, but 2 years later, you'll come back and you might say, oh, there's this variable called global rainfall. I need to know that everywhere. So just as a defensive programming technique, I tend to use all reduces everywhere in preference to reduce. Perhaps you only really need to know the value on the controller process, but using all reduce makes things simpler, and there really aren't any serious performance implications. I think it's a nasty side effect of the SPMD model, where every MPI process runs exactly the same code, that all variables exist everywhere, even if their values don't make sense. And you may forget that. So I think using all reduce is a good programming technique. Error checking. This is something which you might do. You might say, well, check the valid results. I've got a partial value, which is one float. I'll sum it up everywhere. But I know, for example, this summation might be a rainfall, total rainfall. Clearly, the rainfall is less. It has to be positive, or at least a non-negative. So you might do an error check. If sum is less than 0, print error. Okay. This is a dangerous thing to do because sorry, I'm being an idiot here. I've done MPI. So what I'm trying to say is I've done a reduction operation here. Okay, I'm doing MPI reduce, not all reduce. So this summation value is only known on rank 0. Okay, so this is not a sensible thing to do. Okay, what you should do is everyone needs to know the result. So what you see sometimes some people doing is they broadcast. You see people do a reduce and then a broadcast. You should not do this, okay? You should use MPI or reduce. So sometimes you see people, they've done a reduce, then they think, well, I now want everyone to know the result. So for this code to stop correctly, everyone needs to know the value of the sum, so they can all independently terminate execution of the program. But you often see people do reduce and broadcast. Do not use reduce plus broadcast. Use all reduce. This is probably going to be twice. All reduce will probably be twice as fast as this. So reduce plus broadcast is not a good thing to do. You should use all reduce and just get the answer everywhere right from the start. This is something, and this is, I mean, I always say, you know, when you, the most important thing when you write an MPI program is to get the correct result and not to worry about performance too early on. But you should not send lots of small messages. Okay, so you should not do something like this. Okay, I want to send in C. I want to send the contiguous part of an array in Fortran. It would be the first index, and C the contiguous part of the second index. I want to send the n values x naught n, which might be a halo. I'm doing boundary exchange. MPI send this value 1 int to the destination, but I loop over j. This is very, very, very slow. You're sending a large number of small messages. You should send a single message of size n. Okay, so this is fairly basic stuff. We can do a single send of this, and this will be a lot faster than that. Okay, MPI, what we will see after the break, if we look at performance, that the latency, the overhead of sending an MPI message is large. Even on a machine like ARCHER2 with a dedicated network, it is at best in the microseconds, a few microseconds, which is millionths of a second, which might sound like a small amount. Remember, modern CPUs are clocking at multiple gigahertz, so the clock cycle is in the nanoseconds, and so a millisecond, a microsecond, apologies, is thousands of times more expensive than doing maybe a floating point calculation. And so, you know, if there's one optimization technique for MPI, it's do a small number of large messages, not a large number of small messages. Now, this is fairly easy to do because the data is contiguous. But what happens if you want to send in C the first dimension, or in Fortran the second one, where the data isn't contiguous? Well, you use a derived type or a vector. So you do not loop over only. So you cannot, because the data is not contiguous here, if I want to send x00, x10 up to xn minus 10, that's a strided pattern because I'm looping over this index, not this one. But the way to do that is to use a vector. Okay. Now you could. A vector is a strided type, which you have to define it appropriately. But having done that, you can send one vector. Now you could do copy in to a temporary buffer, send and copy out again. Performance is probably not that bad, but it is ugly. And so derived types such as vectors are very, very useful for sending, for ensuring you send a small number of large messages, but doing it in a neat way without explicit copying. This is just when people are learning MPI, you often see them. I have an example where you have to compute pi in parallel, and people write, so you have a loop from 1 to n, and you want to split it up across the processes. And people in there, when they're writing their very early codes, often write a code which is specific to here 4 processes. They assume they're running on 4 processes, so they say, you know, if rank is 0, I loop from 1 to n over 4. If rank is 1, I loop from n over 4 plus 1 to n over 2. And they have 4 code branches. That's clearly a bad thing to do. It's not scalable. However, so you shouldn't write code which only runs on a particular process count. However, it's often easiest to make P a compile time constant. It may not be the most elegant thing to do because you have to recompile your program when you change the number of processes. However, compilation is quite fast these days, and it can make things much easier. It can make defining arrays and such like much nicer if P is a compile time constant. So, I mean, ideally a single executable will run on any number of processes without recompilation. However, you know, if you're developing your own code and the time you can spend in developing the code is limited, having P a compile time, number of processes, the compile time constant is not necessarily a bad thing. However, you have to check at runtime that it's compiled, it's running on the right number of processes. So if you've compiled it for 20 processes and you run it on 10, you have to say, look, I can't run, you've compiled. But you know, it's not necessarily a terrible thing to have P a compile time constant. It can make, especially in languages like C, where array allocation is rather hairy, it can make things easier. So this is an interesting one a lot. So incorrect use of non-blocking. You do see this all the time. This is where you write an incorrect program, which often still runs. Can anyone spot what's wrong with this code? So the ISend is a routine. ISend is non-synchronous send. So I'm just using that as an example. So that is a correct routine, but the no, what do you mean by too many sends, Stephen? That's interesting. I don't quite know what you mean here. There's two sort of things wrong with this code. The first is that I've got this now start compilation. What I'm doing is I'm doing. Okay. No, but this. So okay. So this code would work because I'm not sending to myself. I'm sending to I. Okay, it's actually to the net. There's not a lot, but it's a way to do the way it's specific to the way I'm using non-blocking communications. So what I'm doing here is you should really do this with a broadcast. But what I'm doing is I'm saying if I'm rank 0, I loop over everybody else 1 to size -1. I send them a value, and everyone else receives that value. So these sends and receives do match up because one process is doing size -1 sends, and size -1 process is doing 1 receive. But it's the use of non-blocking which is the problem here. So you're absolutely right. There's no point doing no. You're absolutely right. Okay, right. So you're absolutely right, Yusuf. There's no point. So people overuse non-blocking. So here I shouldn't use non-blocking. There's no need here. However, in a more complicated example, I might need to do it. So yes, so there needs to be some synchronization between this and this. But a barrier is not what you need. What you need to do is you need to make sure that these non-blocking communications have completed. So you need to wait. Every non-blocking communication has to have a wait where you tell MPI, I cannot proceed until this communication has completed. And the important point is that wait does two things. A, it acts like a barrier, Stephen has mentioned, so it makes sure that the program waits until that communication has been completed. But more equally importantly, it allows MPI it knows that communication is finished and that you have waited on it, and it can then free internal resources. So there are actually two problems with this code. One is now start computation. I haven't waited for these receives to complete. I don't know these receives, and they've been issued with that, so I need to have a wait. So we need so there's two problems here. We need to have a wait here, but also okay here. So right, there needs to be a wait here on these received to check they've completed. The other problem is I'm issuing multiple senses. So remember, when you issue a non-blocking communication, you're asking MPI to do something in the future. Could you please send this message sometime in the future? What MPI gives you back is a request. This is returned to you, and that is effectively like a ticket. This is your ticket number or your receipt, your order number for this communication. What I'm doing here is on this, when I do I equals 2, I'm issuing a second MPI send to rank 2, but I'm overwriting the request. And you see that people doing this quite a lot. They are overwriting the request. So it's like they've lost the first ticket. And that is a problem because it means that you will never, ever tidy these things up. You will never, and this is a memory leak. So you see this quite a lot. This code would run, okay? If you were lucky, it would run correctly because you might be lucky and not have the equivalent of a barrier here, not having a weight here you might be lucky enough. But the problem here is that you are overwriting the requests. Okay, these tickets which MPI is issuing you, if you issue here size -1 non-blocking sends, it's up to you to remember size -1 tickets. You can't just overwrite them, okay? And that would lead to a memory leak because MPI would never be able to tidy up free the resources associated with these ongoing communications. And going back to exactly what Yusuf said right at the start, why use non-blocking here at all? Okay, so again, people tend to overuse non-blocking when it's not needed for simple pieces of code like, well, of course, here you should really do a broadcast. But if you need to do a pattern like this, which couldn't be done through a broadcast, you could avoid the complication of non-blocking unless it's performance critical. So you will need to use non-blocking communications down in the depths of your code for halo swapping and things like that. But for setup at the start and then shutdown at the end, I would avoid using non-blocking unless it's absolutely necessary. Debugging, I don't want to maybe labor this point, but I think that what I would say is that debugging is hard. Parallel programs are more, debugging any program is hard. Parallel programs are more complicated than serial programs, and therefore, so writing good, maintainable, verifiable code is even more important in parallel programming than it is in serial programming. So I think the major mistake that people make is whenever their program goes wrong, they assume it's a parallel bug. People say, my program goes wrong on 256 processors. There's some wrong. Well, maybe you've just made a good old-fashioned bug. Okay? Maybe it's just a bug. So check you haven't broken the serial code. Check you haven't made a logic error in your algorithm. Then run the parallel code with p = 1. Then run a small number of processes. It's relatively unusual for a bug to manifest itself only at very large numbers of processes. Typically, if there's a bug in your program, it will manifest itself on a handful of processes, and then it is debuggable. So the first thing you should do if you find a bug in your program is find the minimum number of processes of which that bug or an equivalent bug manifests itself and debug. So it really is almost impossible to debug on large numbers of processes. Yes, parallel debuggers exist. This is a very old linear DDT. It's now called Forge. However, debuggers are powerful tools, but they're very complicated to learn. Old-fashioned verification printing is still a very useful technique, but it's only possible to do in every process if you're running on a small number of processes. And so if you're developing your own code, I would say that that actually often the debugger is not a panacea. Okay, so someone's asked a question here. So I like how they actually polish. So was that well? Yes. So what's probably happening here, Mark, is that that there's a load imbalance. In other words, you've issued a lot of receives. You're expecting data to come in. Okay. So issuing the receives takes no time. Okay. When you issue a receive, you're saying, I would like to receive some data sometime in the future. When it comes in, put it here. So the receive will not take any time. However, when you do a wait any, what you do is say, okay, I'm going to wait until some data is received, okay? And so if it's showing a long time there, it's just showing that there's a load imbalance. That means that at the time you're waiting for the data, it has not been sent yet. So if you'd used a blocking receive, if you just did MPI receive, the profiler would have showed a lot of time in the receive, waiting for the data to come in. Here, issuing the receive is instantaneous because you're saying, sometime in the future, the data is going to arrive, put it here. But it's the wait, which, does that make sense? So so yes, spending a lot of time in wait is not unusual, but it means that there's a load imbalance. It means that you're saying, I'm going to wait for some data to come in, but it's not been sent yet. Yeah, that's a good point. Yeah. So wait any is saying, I have got a lot of outstanding non-blocking receives. Please wait until one of them has been completed, which is a yeah. So this is one of my bugbears, but to stop people, it seems to be people write silent programs that doesn't be. Your program should print things out. I don't want to over egg this thing, but your program should say, hi, I'm running on so many processes. It should say whenever you're doing parallel I/O, it should say and if you've got some iterative loop, every few hundred iterations, it should print out what it's doing. And if someone tells you my program crashed, and you say, where did it crash? And they say, I don't know. Even printing hi running on the program started up. Okay, so just giving general information as to where your program is will give you invaluable information when you want to debug it. And then, yeah, this is my bug. People write raw numbers to the screen. You have to say what they are. Okay, when people print 135.6, what is that? Yeah, you want to print that's the rank, the value of j, that's the value of x. Okay, so you have to annotate your outputs. Okay, it will save you huge, very simple techniques will save you huge amounts of time in the future. I don't understand why people write raw numbers to the screen without any text. So this is why I want to say there's a common mistake people make, that there's a bug, okay, but you change something, you switched compiler, you put a print statement in and it went away. Okay, so there was a bug which you didn't understand, and something changed. As I said, maybe you changed, I used GCC instead of ICC and it went away. I put another print in and it disappeared. Okay, and it now works, but you don't know why. Okay, all is okay. No, it's not. Okay, you have a bug there, and just by I changed the compiler and it went away. Well, no, that means you've got a problem. You have to find, there is a bug, you must find it. If not, it will come later and bite you hard. Okay, so sidestepping a bug is not a good thing to do. Okay, it's useful to know that the bug appears in Intel compiler and not the GNU compiler. That's useful information, but that does not say that means I should use the Intel compiler or the GNU compiler. It says that you should try and find the bug. Okay, and I said debugging is an experimental science. You start with the serial code, you start with the parallel code of one processor, you do it on a small process count. And so for all this to work, you have to have some definition of your program being correct, which for numerical code using floating point numbers can be a slightly subtle question. But you need to continually verify both the performance and correctness of your code on a range of process counts, because you need to pick up the bugs when they first come in. Okay, if you introduce a bug, you want it to be picked up immediately. Now, if you're a modern software developer, you don't have a huge suite of regression tests that run automatically overnight through some continuous integration system. Well, yeah, maybe you do, maybe you don't, but it should be a way. You should achieve that. That would be the ultimate aim. But just running by hand is often better than nothing. I have a whole bunch of things about whether the code is working. I don't really want to go into this in detail, but the big problem in parallel programs is it is very unlikely that the output will be identical for different number of processes. Okay, because when you run a program on different number of processes, the calculations are happening in a different order. Okay, and floating point operations are not associative. A times B times C. A plus B plus C is not the same as A plus B plus C. Mathematically, addition is associative. In finite precision, it's not. So it is important to have some verification results that you trust, but it is quite a subtle question. But you have to accept that it's very difficult to write a program which gives identical with floating point numbers, that you get identical output for different numbers of processes. It is possible, but probably the performance would be terrible. So it's a bit of this slightly off topic here. Optimization, yeah, as you go along, run your code number input dates. So you should debug you should verify your code is correct regularly as you develop it. But you should also verify that the code is running efficiently. You don't want to do something which cripples the performance. So you should keep running your code on a number of input dates with a range of MPI processes as you go along. And then if the scaling is poor, you need to find out what parallel routines are the bottlenecks. And again, this is much easier if you have a separate comms library. Okay, if you run a profiler and it says you're spending, Mark here, for example, you're spending 57% of your time in MPI wait any. Well, if you call MPI wait any, lots of times you don't know where that is. If the profiler says you're spending 57% of your time in wait any, and by the way, 50% of your time in a routine called MPI halo swap, then you know that it's the halo swaps that are doing it. So knowing how much time your program takes in each MPI call is not necessarily useful information because you don't know where it's being called from. So again, having your communications in a separate library makes both debugging and performance optimization easier. It's very easy to think that it's your parallel performance. Sometimes you do something which cripples the serial performance, and you have to work on the serial code. Okay. I will cover Fortran array syntax here. It's a bit subtle. I said that for non-contiguous data, you should use a vector. Okay. So MPI derived types enables Friday data to be sent and received. You don't need, there's no explicit copy in or copy out required. For Fortran, a Fortran program might say, well, why not use Fortran array syntax? I can use Fortran array syntax to select non-contiguous data. There are subtleties for non-blocking operations, which I'm going to cover here. So if I'm a Fortran program and I did this, allocate buff n, MPI isend or isend buff, and then I deallocate it. What's wrong with that? Why is that code incorrect? So I'm allocating a buffer, telling MPI to send it in a non-blocking way. So I'm telling MPI, please send this buffer sometime in the future, okay? And I'll come back and check later if it's been sent. And I'm immediately deallocating the buffer. Why is that a problem? Yes, you cannot deallocate before, because what happens later on, MPI will say, I want to send the data now, and it will find the buffer isn't there. It's a null, and you might get a crash. Okay, so that's hopefully relatively obvious that's wrong. Unfortunately, so non-blocking step may still be ongoing at deallocation. The code could crash or give unpredictable behavior. It's only safe to deallocate them after the matching wait, which is the same thing as saying the receive. Yeah, Ricky is saying that a receive has been put. If you wait on this communication and it's completed, that means the receive has been put. And you get identical issues in C using malloc and free. However, because Fortran has quite sophisticated array handling, this can happen in a non-obvious way. And so the problem here is I do a real dimension mn array, and I say I want to send this second index, which is non-contiguous in Fortran. What I will do is I will just do an array syntax 1 to n. Okay. Now this looks okay, but probably what the compiler does is under the hood, when it sees this before, what it does is it does a copy in, call the function copy out. Okay. So unfortunately, at least in the older Fortran interfaces, the compiler did not know that this function MPI isend had long-term effects. That the compiler is assuming that once this function returns to the main program, everything is completed, and so copy in, call function, copy back out is perfectly legitimate. The problem is we know that this is carrying on after the call returns, and so if the compiler does this, then you've got a problem. So more modern, if you use the Fortran 2008 interface, you're probably safe here. If you use the Fortran 90 interface, you're probably not. It is a subtlety, so you have to be careful if you use array syntax. So it's only an issue for non-blocking operations. Okay, for blocking operations, this would be absolutely fine because when this routine is returned, we would know that it had completed and used and finished all its arguments. Just because non-blocking operations are what you might call asynchronous, they carry on in the background, you get this problem. The advice is avoid array syntax and use vectors. However, this has been solved for more modern interfaces where Fortran now can be told that operations have long-term effects through the, I think is it asynchronous? I can't remember what the attribute is. So there is a variable called MPI subarray supported, which tells you, so if MPI subarray supported is true, then this code will work because the library or does the right thing. Okay, it makes sure that the data is persistent until the operation has been waited on and is completed. So it is a slightly subtle point, but I have seen problems with this, and so I wrote a little test code for this. But there is now if you use the 4.2008 interface, then typically this is not a problem. But if you're paranoid, you should check by checking is MPI subarray supported, true or not. There's a lot here about array allocation issues with C. I don't want to go into this in a huge amount of detail, but the problem with C is that if you do multi-dimensional arrays and you do pointers to pointers, which is the standard way of doing things, then your data is not contiguous. Okay, you have fragmented data, and that's the problem. Both that means that if you allocate two-dimensional arrays in C by first allocating a bunch of pointers to the rows, if you want to call it that, and then allocating the rows themselves, you get fragmented data. And that gives you problems. What you really want is you want to have, so if you have pointers to pointers in your multidimensional C arrays, you really want to make sure your data is contiguous, and by default that won't be true. So this is showing, if you do two-dimensional arrays like this, you basically you have a int double star x, and you malloc some pointers, and then you individually malloc the rows, if you're thinking about a matrix here. Then x points to some pointers which point to the data, but the data is all over the place in memory, and that means that there is no relationship between this element, this element, this element, and this element. I can't use a vector to send that data because I don't know where it is in memory. So again, there is I will provide the routine. There isn't a routine. There's a way of doing this which solves the problem. The problem is you still have pointers to pointers, but you do a single malloc for the data and fudge up the pointers by hand. And I have an example which I actually don't think I've put on the website called Array Malloc 2D, which shows you how to do this. But if you are going to use dynamic array allocation in C with malloc, you have to be careful. You don't do the naive thing of allocate lots of pointers, then individually allocate the data associated with those pointers, because it means that your data is fragmented and your subsequent MPI calls will be slow because you won't be able to use vectors, or you won't be able to broadcast the array as a single entity because it's fragmented in memory. And so you should use more clever dynamic array allocation tricks to do that. And I have an example there. This is stuff which is not relevant. This is really just so yeah. So in C, fixed size arrays hash defined are simple and easy to use, but you need to recompile. Dynamically allocated malloc arrays are more complex. They come from the heap. Variable length arrays are frowned on by purists. This is where you do int x n, where n a variable, not a constant. The main problem is that they come. Whoops, sorry. The main problem is they come from the stack, which is limited size. So if you want to do dynamic array allocation at runtime, you probably want to use some version of malloc, not VLAs, but because they run. So I'm basically saying that in C, if you're going to allocate large amounts of memory for your major arrays, you need to be clever and don't do pointers to pointers to pointers. Make sure your data is actually a single contiguous block. A final one here, which is I'll just slightly more in MPI, message matching is quite subtle. And what if I'm imagine I'm sending an MPI vector, which might be a set of three. It might be, remember, a vector. It can be a non-contiguous block of memory. It has blocks and gaps in it. So if I send an MPI vector, which is, for example, a block of 3 and a gap and a block of 3, what actually MPI does is, at least logically, is it packs that data into a single block of 6. And then on the receive side, so if I send a vector, okay, I send one vector here, I don't need to receive one vector. As long as the receive receives here, say, 6 integers, that is fine. So message matching is slightly subtle in MPI, but allows you to do nice tricks. That if I send this data in flight, the message is just 6 let's say they're integers, 6 integers, and I can receive that in the same pattern. I could receive it in a contiguous pattern. I could receive it as a different vector, as long as I send 6 integers and I receive 6 integers. Those messages will match. They're compatible with each other. The spacing, the pattern, the gaps in them don't matter. And this allows you to do nice tricks. And this allows you to avoid hand copying. Often people copy data, send it, they pack data, send it, and unpack it at the receive side. This trick allows you often to avoid that because, for example, if I have data which I've read in from memory, which is contiguous, but I want to send it to a lot of processes where they want it to be the interior. Often the data I read in from disk is just data, but the arrays I have in memory have halos on them. How do I send that data into there? Well, I can play tricks by sending the data as a contiguous block and receiving it as a vector. So it's a bit of a slightly off topic here, actually, but understanding the message matching rules in MPI, basically saying if you send 6 integers, you can receive them as 6 integers. It doesn't matter how they're padded, how they're distributed, how they're packed. Allows you to do nice things. And what we'll do is if I have time, we'll exploit this when I do the advanced use of data types at the end of the day. So this is maybe I will come back to this. Doesn't make sense now. So the conclusions, I'm slightly okay. For debugging, run on a variety of machines or more accurately run on a different. Debug your code using different compilers. Like compile and check your code is correct using different compilers, but also different libraries, versions of the MPI library. Keep it simple. Don't use non-blocking when you don't need it. Maintain a serial version if you can, which will allow you to always check your code is correct. Don't assume all bugs are parallel bugs. That is the biggest mistake you make. And find a debugger you like. Or if it's your own code, I say actually debuggers are often not as useful as a good test suite and by hand debugging. So probably that was a bit of a butterfly collecting or stamp collecting of lectures. The other lectures will be more focused. But does anyone have any questions about that? Are we still on the? I will just. Okay, so I've lost. I'm trying to. I'm on my laptop for various reasons, and I am slightly lost as to where my control is. Okay, stop here. Okay, so what we'll do is if I go to the timetable, we're going to be back here at in 25 minutes at 11:45. We'll do MPI internal. So okay, so I will check. Okay, so that is it better still to use the MPI vector 243? That's a very good question. I'm old-fashioned. I would do I don't know. I mean, under the hood, MPI is probably doing a copy. Probably, it might be able. It's possible MPI could avoid the copy. Okay, I don't. To be honest, my Fortran is rather old-fashioned. I don't know how Fortran 2008 implements the asynchronous for MPI. It could do one of two things. It could make a copy. It could make a copy, and just make sure that copy was around until or it could do clever things with passing array to script. Because I grew up in a time when Fortran array indexing was not guaranteed to work because the Fortran 2008 interface did not exist when I learned MPI, I would always do the vectors because that's guaranteed always to work. But maybe I'm old-fashioned. Because you might say, well, the compiler is. I don't really know. That's a very good question. I mean, do you mean better in terms of performance or better in terms of code maintainability or elegance? I don't know. To be honest, I would do the MPI vectors because it very much depends. I don't know. I would have thought there's probably fewer copies if you do the vectors. I might be wrong there. My concern is that often the Fortran 2008 interface can be. Fortran is a very challenging language, and I think things can go wrong. I mean, the GNU compiler is a bug that if you pass array subsections, it messes. I would never be. I would if I had a program that went wrong and I was using the Fortran 2008 interface and array syntax, I would always be right. Is there something going wrong here? Is it not quite doing it right? Yeah, but I'm sure if you asked a more modern Fortran programming, they might have a different answer. But the Fortran 2008 interface is great, but it does rely heavily on your Fortran compiler being 100% correct and doing everything correctly. And a lot of areas of the Fortran standard aren't exercised that much. You know, a lot of Fortran programs are pretty old-fashioned. So when people start using modern features, I'm always concerned there could be bugs there that just haven't been exercised yet. So I would go with the vectors, but it's a very good question. I don't know. It'll be an interesting thing to try. Interesting to try. Okay, so I'm going to take a break now. As I said, I'm struggling with multiple